Hello students, welcome to online class. How have you been doing? I'm sure you are doing well. So well done for so far for what you've been trying to do all by yourself. I'm sure you are doing well and you'll be watching the videos, copying the notes, and doing the assignments that have been sent to you on the school website. Please ensure that you always copy your notes and do the assignment at the end of the notes. It's very important to do those assignments because it actually helps you to understand better what you've been taught in the lesson. Very important to all of that. So in this class, we'll be looking at SS1 topic. We'll be treating SS1 topic in this particular class. So far so good. We've treated topics for week 1 to week 5. So in this particular class, we'll be looking at week 6 topic, which is the topic is relative acidity and alkalinity for week 6. That's the topic, which is the pH scale. That's what you are going to be looking at. I've already sent the notes to you on your school website. Please check out the notes, copy them, and then watch this video, and to actually help you to understand. And please, when you are watching the video, try as much as possible not to be distracted. Just try as much as possible to concentrate and put in the best attention you can in it to actually help you. So now, I said we are looking at relative acidity and alkalinity, the pH scale. So now, our learning objective for today are 1, should be able to understand the concept of pH and pH scale, should be able to carry out calculation involving pH and pOH, discuss the importance of pH, state the color change of indicator in different regions. These are our learning objective for this class. So let's look at the pH scale. So the pH scale is a numbered scale from 0 to 14 used to measure the degree of acidity or alkalinity of a solution. Now, there's something important that you need to note here. pH, when you see the word pH, you see that P is in small letter and H is in capital letter. So make sure that when you are writing it, the P is in small letter and the H is in capital letter. What it just means is power of hydrogen or potential of hydrogen. pH, that's what it just means. But like we use that P to represent what the actual meaning is. But back to what we're saying, the pH scale is a number scale from 0 to 14 used to measure the degree of acidity or alkalinity of a solution. Now, in our previous classes where we talked about acid base, and so we said that an acid base substance which produces hydrozonium ion as the only positive ion when dissolved in water. And I always tell you that the characteristic property of an acid is the production of hydrogen ion. So it's that hydrogen ion that actually combines with water molecule to form the hydrozonium ion. So, and then when we talk about bases, alkaline produce hydroxide ion, OH-. So pH scale is used to measure the amount of hydrogen ion in a particular solution, and is a number scale from 0 to 14. So now, a substance with pH value of 7 is neutral, meaning that it's neither acidic nor alkaline, while a substance which has pH value less than 7 is said to be acidic, meaning that it has pH between 0 to 7. Such substances are said to be acidic. Then a substance which has pH values greater than 7, that is between 7 and 14, are said to be basic or alkaline. So this is pH scale, number from 0 to 14. Now let's look at the next thing. Now it means that acidity increases with decreasing pH value. So as pH value is decreasing, acidity increases. While as pH value is increasing, the alkalinity is increasing. So like I said, the pH scale is numbered from 0 to 14. So you have 0 to 14. At 0.7 is neutral, which is the middle point. is neutral. Then between 7 to 0 is acidity, or between 0 to 7 rather is acidity. And we said that as acidity, as a pH value is decreasing, the acidity is increasing. Now, for example, if you have a substance whose pH value is, you have three substances whose pH values are 6, let's say 4 and 1. 1 is more acidic than 4 and 4 is more acidic than 6. So it means that you see, as the value is decreasing, the acidity is actually increasing. While on the other hand, if you have three substances whose pH values are 8, 9, and say 13, 13 is more acidic is more alkaline, sorry, is more alkaline than 9, and 9 is more alkaline than 8. So alkalinity increases with increasing pH value. So at 0.7 is neutral. So like I said before, the pH value of a solution is actually the measure of the hydrogen ion concentration in that solution. So which is why the name is power of hydrogen, pH. So the measure of the amount of hydrogen ion ion in a solution. So the measure of the hydrogen ion concentration in a solution. Now let's look at the mathematical representation of pH. pH is mathematically the negative logarithm of hydrogen ion concentration. Mathematically, so it means that pH is equal to minus log hydrogen ion. Also, it can also mean pH is equal to minus log hydrozonium ion concentration. Now, if you notice, this square brackets, hydrogen ion is just H plus, but when you are talking about the concentration of the hydrogen ion, you put it in square brackets. Hope you are getting it. So hydrogen ion is just H plus, but hydrogen ion concentration, meaning that the amount of hydrogen ion in a solution, you represent it by hydrogen, you represent it by a square bracket. Hydrozonium ion represented by H3O plus square bracket, so hydrozonium ion concentration. So now, if we make hydrogen ion or hydrozonium ion concentration the subject of formula, we have 10 raised to power minus the pH. So hope we get that. So that will give you 10 raised to power minus the pH. Now, going forward, now if for example in a solution you have that hydrogen ion concentration is equal to 10 minus X. So if you take the negative logarithm on both sides, it means that the negative logarithm of hydrogen ion is pH is equal to, now log of 10 is 1. So log of 10 is 1, so is 1 raised to power 1. So your answer will be minus S, because you are taking log of just 10, log of 10 itself. So you have minus S as your answer. So if you minus times minus is plus, so therefore pH is equals to X. Now moving on, so for example, let's use a specific example. If you have hydrogen ion concentration of a solution to be 1 times 10 raised to power minus 2. Now do you notice I have mole per dm cube here. Mole per dm cube is the unit for concentration. That's the SI unit for concentration. So I have mole per dm cube as the concentration of the acid. So 1 times 10 raised to power minus 2. So therefore pH is equals to 2. So just take your answer as 2 when you are giving that value. So the pH of that solution, if you are giving, will be 2. We'll soon see some other examples. Now, for a given solution, in a particular solution, the sum of hydrogen ion concentration and that of hydrozonium ion concentration is equals to 10 raised to power minus 14. So if you take the negative logarithm of all sides, you have negative log pH, negative the hydrogen ion concentration plus negative log hydrozonium ion concentration is equal to negative log 10 raised to power minus 14. So now, therefore, pH is equal to POH. See, we already know that pH is negative log hydrogen ion concentration. We know that. So from that, we can also agree with me that negative log hydrozonium ion concentration is equal to POH, which is equal to 14. So note that. Now, if we make pH the subject of formula, pH will be equal to 14 minus POH, and POH will be equal to 14 minus pH. So now, pH is a dimensionless quality, meaning that it has no unit. pH has no unit. So if you are looking for the pH of a substance, it has no unit. And I told you that concentration is in mole per dm cube. So now let's look at specific example. Our example number 1. Find the hydrogen and hydroxide ion concentration of A, 0.1 mole per dm cube hydrochloric acid solution, B, 0.01 mole per dm cube potassium hydroxide solution, and C, 0.01 M. Do you see this? In this case, we have capital letter M. This capital letter M is also mole per dm cube. Now, if you notice here, I have MOL/dm cube, but here I have MOL dm cube raised to power minus 3. Because this slash is not here, that's why the dm cube is now minus 3. Hope we are following this. Then OH, yeah, I said that M means mole per dm cube. Now, moving on, let's look at the solution for that. So, for number 1 mole of hydrochloric acid will produce 1 mole of hydrogen ion. Now, in solution, it will produce 1 mole of hydrogen ion. So, therefore, in 0.01 mole per dm cube solution of hydrogen chloride, you now have hydrogen ion is equal to now 1 mole produces 1 mole of hydrogen. So it means that in 0.1 mole per dm cube solution of hydrogen chloride, you have 1 times 0.1, which is will give you 1 times 10 raised to power minus 1 mole per dm cube. So that is the hydrogen ion concentration. 1 times 10 raised to power 10. 1 times 10 raised to power minus 1 mole per dm cube is the hydrogen ion concentration. Why? Now, remember we are asked to look for the hydrogen ion concentration and the hydrozonium ion, hydroxide ion concentration. 2 things we are asked to look for in that particular question: hydrogen ion concentration and hydrozonium ion concentration. Now, look at that. Sorry, just a moment. So we have, if we are to look for this, you know from the formula that hydrogen ion concentration times hydrozonium ion concentration give you 10 raised to power minus 14. So give you 10 raised to power minus 14. Therefore, you already know that the hydrogen ion concentration is 1 times 10 raised to power minus 14. So if you make hydrozonium ion the subject of formula, you have hydrozonium ion is equal to 1 times 10 raised to power minus 14 all over 1 times 10 raised to power minus 1. So hydrozonium ion is now equals to 1 times 10 raised to power minus 14 plus this minus move crosses the division sign, becomes plus. So hydrozonium ion is 1 times 10 raised to power minus 13 mole per dm cube. Now let's go back to the question B. We are calculating the hydrogen and hydroxide ion concentration. Please, hydroxide ion concentration of 0.001 mole of potassium hydroxide solution. Now, let's go to that. That is our B. So, for B, just a moment. So, for B, we'll have, let's look at that. B. So, KOH, which is potassium hydroxide, we ionize completely to give us 1 mole of hydroxide ion, not hydrogen ion, because it's a base, an alkaline. So it will give us hydroxide ion, not hydrogen ion. So it means that the hydroxide ion concentration will be 1 times 0.01, which is the concentration of the base, to give us 1 times 10 raised to power minus 3 mole per dm³. Hope you are following that. So that's the hydroxide, the hydroxide ion concentration. In this case, we've got the hydroxide ion concentration first. Then let's get the hydrogen ion concentration. Hydrogen ion times hydroxide ion concentration is equals to 10 raised to power minus 14. So we now have hydrogen ion concentration. If we make, we equate the value of hydroxide ion concentration, which is 1 times 10 raised to power minus 3, equals to 10 raised to power minus 14, making hydrogen ion the subject of formula. We have 1 times 10 raised to power minus 14 over 1 times 10 raised to power minus 3. So hydrogen ion will be when minus 3 crosses the equality sign, we have 1 times 10 raised to power minus 14 plus 3. This is just standard form. So hydrogen ion concentration will be 1 times 10 raised to power minus 14 minus 11 mole per dm³. That's the hydrogen ion concentration. Then number C, we are asked to look for the concentration of hydrogen ion and hydroxide ion concentration of H2SO4. Now, when H2SO4 ionizes, it will produce 2 moles of hydrogen ion. Unlike hydrochloric acid, it produces only 1. But now, why? Because H2SO4 is a diabasic acid. Remember, I talked about basicity of an acid, that is the number of replaceable hydrogen ions. So when it ionizes, it produces 2 hydrogen ions, meaning that in 0.01 molar, remember I told you molar means mole per dm³. So in 0.01 molar H2SO4, it will be, the hydrogen ion concentration will be 2 times 0.01. So which will give you 2 times 10 raised to power minus 2 molar. That's in standard form. Always put your answer in standard form. So let's look for hydroxide ion concentration. So hydroxide ion concentration will just be 1 times 10 raised to power minus 14. Why? Because we know that hydroxide ion, the sum of when you multiply hydroxide ion by hydrogen ion, you get 10 raised to power minus 14. So you now have hydroxide ion to be equal to 1 times 10 raised to power minus 14 over 2 times 10 raised to power minus 2. 1 over 2 is 0.5. That's why you're having 0.5 there. Times 10 raised to power minus 14 plus 2, because when minus 2 crosses the equality sign, becomes plus in standard form. So we now have our answer to be 5 times 10 raised to power minus 11 molar. Remember I said molar means capital letter M, also means mole per dm³. So it's the same thing. So moving on now, example number 2 said the hydrogen ion concentration of 2 solutions. Now, let me quickly make a point here. This first part that we just talked about, measuring the hydrogen ion or hydroxide ion concentration in a solution, right? Yes. So in this case now, so we will see how we can apply that in solving questions. Now, in this other one, you are given 2 solutions whose hydrogen ion concentration are 0.01 mole per dm³ and 5 times 10 raised to power minus 9 mole per dm³. Sorry, mole per dm³. So we are asked to find the pH of each solution and state whether the solutions are acidic or alkaline. So for the first one, hydrogen ion concentration is 0.001, and if you express that in standard form, it is 1 times 10 raised to power minus 3 mole per dm³. Hope we are following that. So it is, because in standard form 0.001 is 10 raised to power minus 3. So if you take pH is equal to the negative log of 1 times 10 raised to power minus 3, which is equal to 3. Remember when I said that if you are given a solution and the hydrogen ion concentration is equal to 10 raised to power minus anything raised to that power, you take that power as the pH. So therefore the pH is acidic. You don't need to use a calculator for this. But if you want to be so sure, look for log 0.001 to give you 3. So you have 3, and then that for the pH is 3. So we are also asked to state whether the solution is acidic. So, if a substance has pH value of 3, that is between 0 and 7, so less than 7, so that means the solution is acidic. Next one, for the next question, we are looking for the pH of 5 times 10 raised to power minus 9 mole per dm cube solution. So now let's look at that. We have the hydrogen ion concentration is 5 times 10 raised to power minus 9 mole per dm cube. So therefore, if you take the negative log of that value, 5 times 10 raised to power minus 9. Now, how do you solve this? Now you have 5, a number, times 10 raised to power minus 9. Remember we said that, so you just said that this is 9 already, right? So log of 5 is 0.69969 something. So approximately we have 0.7. So that is the log of 5. So we now have that if you work that out, you have 8.3. Therefore, pH is equals to 8.3. Now, you agree with me that this pH is greater than 7. So the solution is an alkaline. Hope we are following this. So next, we look at number 3. Calculate the pH and pOH of 0.02 mole per dm cube tetraoxosulfate 6 acid. Now, in this particular question, we are given a specific acid, tetraoxosulfate 6 acid. So remember when we solved the question, you know that 1 mole of tetraoxosulfate 6 acid give you 2 mole of hydrogen ion. So it means that you multiply 2. That's why I said H2SO4 is a dibasic acid. The solution will produce 2 times 0.2. That's the concentration of the acid. So because it produces 2 hydrogen ion, it will now produce 2 times 0.02 mole per dm cube hydrogen ion. So it means that the hydrogen ion concentration is equal to 0.04 mole per dm cube. So therefore, pH is equal to minus log 0.04. So if you take the log of 0.04, it will be equal to 1.4. 1.4, that's the pH of the solution. Now, again, you were asked to calculate the pOH. From our formula, pOH is equal to 14 minus pH. So therefore, pOH is equal to 14 minus 1.4, which gives us 12.6. Okay, good. Let's move on. Next thing, we look at number 4 example. So what is the pH of a 0.02 molar sodium hydroxide? Now, you are given a sodium hydroxide, which is an alkaline. An alkaline will produce OH minus, will produce hydroxide ion, not hydrogen ion. Remember, pH is the measure of the hydrogen ion concentration. So if we get the pOH of this solution, we can actually get the pH from there. So 1 mole of hydrogen ion, sodium hydroxide will give us 1 mole of OH minus, that's hydroxide ion. So it means that the concentration of hydroxide ion, now hydroxide ion in square bracket, I always said is equal to 0.02 N. Now, because why? We see 0.02 molar, so we represent it with capital letter M. And I told you that that capital letter M is also equivalent to mole per dm cube. So if you take, so it means that the pOH, which is negative log 0.02 is equal to 1.7. So if you take log, negative log 0.02, you have 1.7. So therefore, pH, which is the actual thing we are looking for, is equal to 14 minus pOH. So pH is equal to 14 minus 1.7, which is equal to 12.3. That's the pH of the solution. So did we get that? Yes, I'm sure we do. Now, lastly, number 5 question, it said, what is the hydrogen ion concentration of a solution whose pH is 4.4? Now, in this case, you are given the pH, and you are asked to look for the hydrogen ion concentration. So it means that 4.4 is equal to minus log hydrogen ion concentration. So if you take multiply both sides by minus, you have minus 4.4 is equal to log hydrogen ion. Now take anti-log of both sides. You now have anti-log of minus 4.4 is equal to hydrogen. Now use your calculator. The hydrogen ion concentration is 4 times 10 raised to power minus 5 mole per dm. Now, do you notice when we are solving for pH and pOH, it has no unit, but when it comes to hydrogen ion concentration, the unit is mole per dm. So always make sure you put the unit of hydrogen ion when you are talking about hydrogen ion concentration. But for pH, it has no unit. So that is for that. Now let's look at the importance of pH. So why is this thing very important? Now, for normal functioning of the body, it is important that our body maintains certain pH. For example, there is a acidic pH is needed in the stomach for digestion of food, while alkaline pH is needed in the intestine for digestion of food. Then for blood functioning, there is a specific pH that is needed in the body for the blood. The blood has a certain pH for the blood, so for the body to function very properly. So if there is a deviation from those pH values, it leads to ill health. So it can lead to certain malfunction of the body. Then look at this scale that I have here. I have acid. So you see gastric acid. That's the pH found in the that's the acid found in the stomach. Is in pH 1. If the pH becomes less than this or greater than this, the body will be malfunctioning. Now let's take another example. Look at milk. Milk has a pH of 6. Black coffee has pH of 5. Tomato. So different fruits and different things that we use at home, they have certain pH. And if the pH is greater than or less than for such a substance, there is a something. It's irregular. Even in agriculture, pH is also important. If the soil pH is not goes beyond the normal one that is needed for a particular plant, the plant will not do well as such soil type. So the farmer will want to maintain the pH for which the soil, for which the crop can actually do well. So it is also pH is important in many industrial processes. For example, when they are producing milk and the pH is less than 6, maybe the pH is less than 6, maybe the pH is 3. That means that milk is very acidic. So the industrialist will want to regulate such pH before they start selling the milk out to consumers. Even black coffee, if the pH is beyond the required amount that is needed, they will try as much as possible to regulate it so that it can get to the end user. So pH is very important in our day-to-day life. Now next, we look at another pH scale. You see increasing acidity. Battery acid is very acidic. Lemon and vinegar. You see, acid rain is as a result of pH between the pH of the water between the pH of 2 to 5. Then normal range of precipitation pH, milk which is 6. Normal range of stream pH. Remember, water is neutral. So water should be pH of 7. Baking soda, seawater, milk of maga, ammonia, and light. So different substances with their various pH. Now, adult fish will die if the pH is in this range of 1 to 5. So fish production will be affected. So the pH needs to be between 6 or 7 for fish to actually do very well. So pH is actually very important in our day-to-day life. Now, next thing we are going to look at lastly is our indicator. Indicators are dyes or substances which show different color according to the pH of the solution. Now, the commonest one you can relate with is the one where we said that acid turn blue litmus red. Yes, you heard that when we were talking about acid, and base turn red litmus blue. So that is an indicator which is showing those color changes due to the pH of the solution. So an acid is showing that is turning that blue litmus to red because the pH is between 0 and 7, while a base is turning, or an alkali is turning that red litmus to blue because the pH is between 7 to 14. Hope we are understanding this. Now, let's look at some other common pH. We have litmus itself. Now, litmus paper is in paper form, but litmus is a solution. Methyl orange is also in solution. Phenolphthalein is in solution. Methyl red is a solution. So you have a different pH. Litmus is between 5.0 to 8.0, which is between acid and alkaline pH. In acid, it will be red. In alkaline, it is blue. Then neutral, it will be purple. Methyl orange is 2.9 to 4.0. That's acidic pH, which is acid, it will give us pink. Alkaline, it will give us yellow. Neutral, orange. Phenolphthalein, 8.3 to 10.0, which is alkaline pH. So colorless in acid, pink in alkaline, colorless in neutral solution. Then methyl red is 4.4, sorry, to 6.3, which is acidic pH as well. Red in acid, yellow in alkaline, and orange in neutral solution. So these are common indicators. So they are actually used to measure whether a solution is acidic or alkaline. So depending on the color that the substance gives, you will know whether a solution is acidic or alkaline. So this is where we are going to end the class for today. I hope you've gotten all that I have said so far. Please try as much as possible to play the video 2 or 3 times, then so that you can get a better understanding of what I have said so far. It's very important to do that. And please send me your question via the school link on the school platform, and I'll answer you as soon as I get them. And also, you can also call me or send me send me the message via WhatsApp, and I will answer you as soon as I get them. Thank you very much for listening. I'll see you in the next class. So until then, stay blessed. So bye. I'll see you in the next class. God bless you.